Hey, thank you very much, folks. Sorry about the slight delay, but it's great to see so many people here. I'll be very brief. David's great at introducing his subject area, and I couldn't do it any better than David will do it anyway. But David Battisti is a professor, visiting professor on a Carnegie Fellowship from the US, based at Edinburgh, but also doing peregrinations around a number of Scottish institutes, meeting people, happy to talk about his subject area. David is based at the Tamaki Endowed Chair of Atmospheric Science at the University of Washington in Seattle. Has a long history of dealing with climate change, ocean interactions with the atmosphere, and has particular interest in the way that sea ice and land ice affect that. My introduction to David was a few weeks ago at a seminar, an evening seminar in Edinburgh, looking at the impact of climate change on food security. And I've been to some very, very boring talks on that subject in the past. David did an amazing job of making it interesting, illuminating, and extremely sobering. Hopefully in January, David will come back and do a full public lecture in St Andrews, and I would urge you to go to it because it is a really excellent introduction to the way that all these things interact and the way that we should be clearly thinking about what sort of impact they'll have, certainly on our lives, for most of us anyway, before we die. So on that note, I will hand you over to David, and hopefully today's talk won't be quite so sobering.
Actually, food security is, thank you. Food security is one thing that actually does worry me about climate change. In fact, that's really the only thing that really worries me about climate change. Let's see, I might sit down occasionally during the talk because I have a back that's not good. In fact, I couldn't even stand up till about 2 days ago. But it's doing great right now. See how long it lasts. And ask me questions all through this thing. It's like an hour. Is that typical here? 1 hour? Okay. Ask me questions whenever you want to, and I'll kind of adjust material as I need be. Let me see. This work's done with Xin Ding and Eric Steig at the University of Washington. Eric's also on sabbatical at the University of Edinburgh right now. And I guess there can be two titles to this. One is the impact of the tropical Pacific on both polar regions. You know, these really remarkable trends you see in Antarctica, in the Arctic today, I think you can definitively say are forced by trends in the tropical Pacific. Why there's trends in the tropical Pacific is another question, which I hope to get to at the end of this. The other way, yeah, so you could just look at the importance of the tropical Pacific for reducing uncertainty and projections of climate change. Are these trends that we're seeing, and we have seen over the last 30 years in the tropical Pacific, are they due to anthropogenic forcing? Are they due to natural variability? I'll argue that you can't actually answer that question right now, but it is answerable. But it's not, you can't do it within the context of the way IPCC works. And I had tried it. So it's kind of a partly a summary of science results and partly kind of a plea for doing business in a different way than IPCC does it. So stop me at any time. And I bet you this is a pretty diverse audience. So I'm going to say a few things about, the first part is just what El Nino is, because that's changes in the tropical Pacific that are communicated globally. And we see trends in the tropical Pacific that look a little bit like El Nino, trends, same pattern. Maybe different physics, maybe the same physics. So we'll talk a little bit about that, and then about how the trends impact the two poles, and in the hypothesis, and then how you could test the different hypotheses. Okay, so how many people are really familiar with El Nino? Really familiar? A couple of people. How many people are sort of familiar with it? Okay, how many people don't have any familiar with El Nino? It's okay. It's okay. Yeah, okay, good. All right, I'll say just a couple of basic things about what it is. First of all, it's due to a natural physics that's not forced by increasing CO2. It's been there for, as far as we can know, for at least the last 3 million years. We have had El Nino phenomenon, and maybe longer. And it's due to coupling between the tropical Pacific and the atmosphere and ocean, right, in the tropical Pacific. So here's the, let's see, that's it. Here we go. Here's a normal situation. This is a cross-section. Here's Australia. Here's South America, North America. This is the sea surface. This would be like temperature. So it's warmer in the western Pacific than it is in the eastern Pacific. You have trade winds blowing from east to west. How many people know about upwelling in this room? Ah, good, okay. Trade winds blow, I'm on the equator, trade winds are blowing from west to east, right? Upwelling, right? Northern hemisphere, it's to the north. Southern hemisphere, it's to the south. On the equator, there's a crisis, right? Water comes up from below. It's nutrient rich. It's a lot of productivity, but it's also cold. So when the trade winds blow here, they basically bring up cold water from below. So and they're pushing the thermocline down here in the west. So the water in the west is warm, and the water in the east here is cold. And the winds respond to that, increasing, that's a pressure gradient in the atmosphere, and the winds actually strengthen. This is called a Bjerknes feedback. For reasons that I don't want to go into today, there's times where this feedback weakens, right? Either because the atmosphere changes or the ocean changes or both. And that the warm water extends all the way into the Central Pacific, and the rain associated with that shifts into the Central Pacific. And the rain is actually just condensing water vapor, which releases latent heat in the atmosphere, and that's what forces the atmosphere, right? So basically moving the rainfall from here to here is effectively like changing where you're dropping stones in a pond, right? It's expanding the atmosphere. Here it's expanding the atmosphere here, and waves go out. Here it expands the atmosphere in the Central Pacific, and waves go out, but they're going out from a different place now. So the far field effects, like where the waves are coming into the shore, like North America, for example, are in different places, right? So you have these El Nino conditions, and that here, and La Nina is kind of the opposite. So El Nino, so it's warmer than normal here, and La Nina, when it's colder than normal, the trades are stronger than normal. Is that okay? I'm not going to get much into it, other than that, here's the typical picture of temperature anomalies with an El Nino event. It's warm in this whole region from the date line to the basically South American coast. Within 5 degrees of the equator, it's warmer than normal by about 1 degree or 2. It's colder over here. And where it's warmer, it's also wetter. So these are rainfall anomalies. Warm, wet here. Over here, it's a little bit cool, but it's much drier than normal. So this pattern of ocean temperature here is indicated by what's called Nino 3.4 cold tank. It's just a measure of the temperature in this box. This is a measure of the sea level pressure difference. When the rain falls over here, it's lower pressure here and higher pressure here. So this is this pattern of pressure anomalies in the atmosphere. And that the difference between pressure here and here is an index for the atmosphere circulation called the Southern Oscillation Index. So El Nino is, or ENSO is El Nino, E-N. Southern Oscillation, S-O, ENSO, right? So why do we call it ENSO? Why don't we call it El Nino? Because in the atmospheric community, in the ocean community, now we call it ENSO, not El Nino or La Nina. It's because they're coupled. So I'm going to show you a time series of the sea surface temperature here and a time series of this atmospheric pressure pattern here, which goes with this precipitation pattern here. And there they are, 1940 to 2000. The blue one is the measure of the ocean temperature, and the red one is the measure of the atmospheric pressure fields. And what do you think? If you know one, you know the other, right? Correlation is 0.93. So what it tells you is that in the tropical Pacific, the atmosphere and the ocean are so tightly coupled that once you know one, you know the other. But it means if sea surface temperature changes, so does winds. If the winds change, so does sea surface temperature. So this is a phenomenon that results because of the coupling between the atmosphere and the ocean in the tropical Pacific. Lots of other things going on in the climate system, but this is fundamentally due to the coupling between the ocean and the atmosphere in the tropical Pacific. Okay. It's the largest source of year-to-year interannual variability in the climate system. Impacts are nearly global. So here's this picture here of rainfall anomalies in the central tropical Pacific, and then there's this kind of wave train that comes out here. These actually go along great circle routes in the atmosphere. And there's wave trains. Basically, it's because I'm now raining here, which means I'm condensing energy, vapor here, which releases heat to the atmosphere, which expands the atmosphere, and waves go out, right? Those waves are associated with wind changes, right? And the wind changes, therefore, are associated with like temperature changes by advection and also precipitation changes. So if you look at a picture, yep.
So internal variability means you're not adding something to the picture.
Yeah, you don't have to add.
Just the current state of concentrations of gases.
Yeah, if you had
everything.
Exactly. So you just fix CO2. You don't allow any volcanoes to go off. You don't allow any sunspots, and this happens. So it happens. If you actually interesting, if you take an ocean model, not all almost, but take an ocean model and you force it with the annual cycle of winds, and you say, do I have El Ninos? The answer is no. If I take an atmosphere model and I force it with the annual cycle of sea surface temperature, I say, do I have southern oscillation? The answer is no. If I couple them, do I have both? And sometimes the answer is yes. Not always, right? Because the models, I'll get that. Go ahead a little bit. Good question, good question. Okay. So Here's a picture of the typical Northern Hemisphere winter anomalies you get during El Nino events. And this one, here we go. So it's drier over here, it's wetter over here. Why it matters if all of these spots here that I've looked at are statistically significant, with the exception of that one. I can't figure out why that one is there. But it's drier than normal here, it's warmer than normal here, it's wetter than normal through here, it's warmer than normal here. Right? This is statistically, these are very robust statistics. And this is because when you change where it's raining in the tropical Pacific, you change this pathway of information leaving the tropical Pacific to the rest of the globe. Okay. So almost all of the high-end climate models used to project the climate response to increase in CO2, the IPCC models. Everyone know IPCC? It's okay? Good. Have a very poor representation of ENSO in their control run. So if you just look at those models before you start increasing CO2, just take them in the modern day CO2 values, or take them in pre-industrial. You say, do I have something that looks like an El Nino? The answer is not, if you're honest, right? Theories of ENSO and 25 years of modeling work demonstrate that the spatial temporal structure of ENSO is extremely sensitive to the tropical mean state, right? The climatology. The way I think about this is plucking a guitar string. You know, you can pluck it light, you can pluck it hard. You're going to get the same pitch out of it, pretty much the same pitch, right? But if I make that guitar string really long, right, stretch it out a little bit, I'm going to get a different pitch, right? I'm going to get a different set of patterns of oscillations in the string, right? And effectively, if you start with a different mean state, you're starting with different strings, different strength of strings, or different lengths of strings. And so what the system does when it kind of gets stochastically forced by weather is different. It looks different. So the structure of the mean state, the fact that you have Eastern Pacific is colder than the Western Pacific, the convection wants to be in the West more than it does in the East, is really critical. If you start with a mean state that has no East-West temperature gradient across the equator, you never see El Ninos in a climate model. If you start with one that's too strong, you see something that's got a lot of action in the Central Pacific, but it's not the same physics as what we see in the observations at all. In your model, you would call it your El Nino because that's what you have, right? But it's not the same physics as nature. Okay, so and this goes back to actually the very first models that were producing El Ninos, 1987, Steve Zbiak, Mark Kane, and just over and over, there's hundreds of papers now that talk about how sensitive that when you couple the atmosphere and the ocean, how sensitive what you get in the end is, your El Nino or your coupled variability, how sensitive it is to what the mean state looks like to start with. Right? Is everyone on board there? It's okay. Almost all of the CMIP5 models have strong biases in tropical Pacific climatology. So here's a common one, and it's a fatal one. It's precipitation. If you look at where in the mean the precipitation is, which also tells you where the warm water is in the mean, pretty much. Here's a map of the multi-model mean, so average of over all the IPCC climate models, and this one is IPCC last year, so that's the most recent one. This is the average precipitation average over all the climate models, and you see it's rainier in the tropical Pacific, in the tropics, the blue, dark blue here, than it is in the high latitude. You see the storm track here in the North Atlantic, right? But here's the multi-model mean bias. And that is, if I average over all the models and I subtract the observations, this is the error, right? If I average over all models. So you might think some models give you, you know, a little bit less rainfall, a little bit more rainfall, but no, that's not it. The models are actually telling you there's a pattern to this error. And these numbers here are 3 millimeters per day, right? The observed is 8 to 10, right? So this is a big error, right? And more important, it's actually telling, look at the pattern of the area. There's two bands of more rainfall here and less rainfall here. So unlike in the real world, we have one band of localized convection in the tropical Pacific. In most climate models, you have two. And that's a really different climate. Okay? Here's the multi-model mean error. So if I take the error, it's the difference between my model and the observations, and then I take the error between the difference between some other model and the observations, I just average those errors. This is the error in terms of the percent of the annual precipitation. Brown is 100%, right? So these are really profound errors in where it's raining, and therefore it's really profound errors in where the wind is blowing and what the trades look like in these models. So no surprise, climate models have weird things like in them that a modeler might call ENSO, but it's not the same physics as in nature. Okay. So here's a placeholder. That's the first EOF. How many people know EOFs? Just a few. Okay, so it's a mathematical technique of saying I have all this data. I'm looking for a set of patterns that explain most of the variance. And the patterns have to be orthogonal. It's not that critical. It's just think about it as the main thing you see in the data set. And actually, I don't care that you see this, which you probably can't see, but each one of those panels is for a different climate model. And if you just say, okay, what do we actually know about El Nino from observations? Well, here are things that we know robustly based on the data. We know how much variance. We know what the variance of the tropical sea surface temperature is. We know what the variance in the precipitation is. We know what the pattern of the sea surface temperature anomalies look like, the typical patterns. We know the strength of the feedback between if the winds blow faster, what's the temperature of the ocean. We know all these things really well from observations, and we know reasonably well the spectrum of Nino 3.4. If you just say just those 5 things, how many of these climate models get those 5 things right? And the answer is 1. Okay, not a surprise. Okay, and this was in the IPCC 2007, so it's AR4. But if AR5 is the same thing. Okay, I'll show you a picture of that in a second. Typical problems with the model ENSOs include 2-year periods. Okay, that's one model gives you an ENSO every 2 years, perfectly. Right, observations say, it's between 3 and 7 years, and the spectrum is really kind of messy. There's a peak there, but it's kind of like a weak peak. 2 periodic is a very common problem. 2 nonlinear or bimodal, the observations tell you that the anomalies are kind of Gaussian around the mean, and a lot of the models are bimodal. They say, I want to be El Nino or La Nina, and I don't like it being in between, which is exactly the opposite of the observations. Maximum amplitude in the Central Pacific, right, which is not right. It should be in the Eastern Pacific. Sea surface temperature variance in the Western Pacific equals that in the East in the models, and that's really wrong because there's actually no change in the sea surface temperature in the Western and Tropical Pacific to speak of. Each of these modes is described by a fundamentally different coupling between the atmosphere and the ocean. What that results in, for example, there's something called the mobile mode, which is actually what the GFDL ENSO is. It's actually a destabilized oceanic Rossby wave. These details are not important. The important thing here is that these beasts that give rise when you couple depend on the mean state, and the mean states are so different that they give you this whole zoo of animals, but none of them look like the real ENSO. So why would you expect a model to tell you how ENSO is going to change when it doesn't start with an ENSO in the first place? Right? Several GCMs have no variability in the tropical Pacific. There's other problems. Okay, so if you just say, why is ENSO so bad? The leading candidate is unrealistic mean states in the tropical Pacific. Have things improved? This is just one picture from the CMIP5, so last year's model. Every gray circle is from 2007 CMIP models, and then the colored ones here from different CMIP models, the AR5 models, the ones used last year. So these are 5 years differences in models, and what's shown here is just the precipitation variability you see in the central tropical Pacific. And here's the grays. They're all over the place. Here's the observed answer right here. If you take the average of all the models, it's pretty, it's pretty low. The average of all the models is about 50% too low in terms of variance, right? And then here's the models from just in this one index from the last year's model. And there's really been no improvement. And this is not a surprise, right? No one expected this. No one, if you're into ENSO theory, this was not a surprise. In fact, if it was any better than this, you would be surprised. The theory's probably wrong, but there's a lot of evidence that theories works really well. Okay, so only 2 out of 25 models have ENSOs that don't violate the 5 robust observational constraints. Just the top 5 that we know from observations, right? Okay, so this suggests that you shouldn't use these models to understand how ENSO will respond to increased greenhouse gases. It means anywhere where you're impacted by ENSO, you've got a problem if you want to understand how the future climate's going to change. For example, Southern California, right? It turns out that quite a chunk of the rainfall that you get in Southern California is associated with El Nino events, right? So if I if I have a model that has no El Nino, La Nina cycles, that model is going to be unusually dry in Southern California because you don't have El Nino events to make it wet. That's what brings the rain in Southern California. Of course, anywhere where you don't have, if you don't have ENSOs, the teleconnections that tell the information about how the climate's going to be vary from one year to the next in the future in, say, the Pacific Northwest, or in Mexico, or in Central America, or South America, or Indonesia, or Southeast Asia, is going to be off, right? This is sounding bleak, doesn't it? The food talk is even bleaker than this, actually. Okay, so and the basic problem is that the models start with this mean climatology. It's so far off. And by so far off, it's like how much error can you afford? If you're off by just a ½ degree C in the Eastern Pacific, that's a disaster for ENSO in terms of the climatology. Now that's tough, right? It also means determining how ENSO changed in the past from paleo records is also tough because you have to know the mean sea surface temperature within at least a ½ degree C, which is a very tough thing to do from a proxy argument. So it's a really hard problem. Okay, why does it matter? Well, you know, no one lives in this tropical Pacific. I just argued that if you live in a lot of places like Southern California, you care about this. If you live in Mexico, you care about El Nino and about how El Nino will change due to global warming. Let me just show you two examples that I think are really important examples to bring up because they're kind of iconic in the discussion of climate change. Okay, that's one in Antarctica and the other one is in the Arctic. So here's a map of the change in the elevation of ice sheets around Antarctica over this, I don't know, 25-year period here. No, 15-year period. And yellow means almost no change, but then you see blues here. It means a wasting of about 6 meters a year. The ice surface is declining. If we blow this up here, oh, it didn't happen. Am I out of range or something? Ah, there we go. So let's look at this thing here. This is West Antarctica. This is where these trio of ice shelves are that come floating out to the sea. Pine Island Glacier, Thwaites Glacier, and I can't remember the other names, are over here. And these are all thinning at an incredibly rapid rate. And the reason why they're thinning is because they're actually accelerating out to the ocean. And there's these ice shelves that are going out into the ocean. And of course, that's a big part of like how much sea level rise is going to happen because this is ice that's draining off the continent right into the ocean. It's going to melt and raise sea level. Here's another trend in West Antarctica. And you can see here all through, here's the Ross Sea and all through West Antarctica here, this is a warming of about 1 degree Celsius per decade, actually, in this region here, okay, over this time period. Okay, good. Okay, now why this matters, or what the deal here is, if you start with, here's the ice sheet, right? And here's this so-called grounding line. And what happens is basically the grounding line, you know, with some text, buttresses the ice shelf. So you have this ice building up from behind, pushing out ice out to sea here. But this thing gives you enough strain in this thing. So eventually the strain in the ice is balanced by the pressure gradient. And you end up with this happy medium where the strain is balanced by pressure gradient. And there's a little bit of ice going to sea all the time, right? And here it is going out to sea. Right, these ice shelves, and they're floating basically. Here's the ocean underneath it, and there's some melt obviously when the water is in contact with the ice, the bottom of the ice shelf. So this is actually what's going on now. These ice shelves here, this one, are actually decreasing here, not because there's been surface melt. It's because they've become destabilized in ice. This grounding line here that's been melted back off of the grounding line. So warm water's come in, melted this down below, melted it off this grounding line, and there's some theory and there's observations that suggest once you get off a grounding line, it's unstable and it will continue to melt back until it finds the next topographic ridge. Right? But if that's the case, it means there's no longer any strain here holding this pressure gradient back and ice just surges out. And that's why the ice elevation is dropping here. It's because ice is surging to the ocean. But why has it all of a sudden gotten warm here? Right? So the ice sheet no longer buttress, accelerates towards the ocean, thinning in the process. and the ice sheet is unstable, and it retreats to the next grounding line. Estimates are a 1 degree C increase in water temperature is about a 10 centimeter global sea level rise in 100 years. I didn't make that estimate. That comes from these glaciology papers. Right? But that's not trivial. 10 centimeters is about a 20–25% of what you get just due to the thermal expansion of the fact that the climate's warming, ocean warms and expands, right, and sea level goes up.
Is that 1 degree at the sea surface or down the bottom?
1 degree here. 1 degree increase in the water temperature there. Right, and so this is the question is, why is this, and this has gotten warmer, and the question is, why has this gotten warmer? And it's not because increased greenhouse gases. Well, I mean, it might be, but the pathway to that is really complicated. It's not because the ocean is warmed up here and it's kind of bleeding down here and it's getting under here, because there actually is no change in water temperature here. That's the observations. There's no trend, right? But the water temperature down here has increased by a lot. Okay? Okay? So here's these glaciers again. These 3 glaciers here. This one's already become destabilized. And here's a picture of an ice. I was going to put Scotland here. Not Scotland, but I think this is kind of Fife. I mean, it's 700 square kilometers, right? Isn't that kind of Fife type scale? Maybe not all Fife. Maybe just the vacation side of Fife, I guess. But it's big. These are big chunks that are just dropping off this ice shelf as it's accelerating to the sea, right? And floating, right? So already the estimates of this Pine Island Glacier will add 3.5 to 10 millimeters to the sea level rise over the next 20 years, just from that destabilization. And there's other ice sheets here that can become destabilized if there's enough melt back. Okay? So here's the surprising thing is, let me work your way through this and we'll get to the surprising thing. These are trends, or epochal differences. They say the late 1990s to 2000 minus the 1980s to mid-1990s. And we did these differences just because the atmospheric data is only really good back to 1979 in the southern hemisphere. This limited data. When the satellites kicked in, we had good observations to say what the atmosphere looked like. So if you look at these differences, like sort of trends, if you want to think of it that way, here's the change in sea level pressure. And so this is a shift. This is a 3 you guys are hectopascals or millibars? Millibars? Millibars, good. Okay. Happy. 3 millibar increase in pressure here in this, taking these kind of decadal differences here. This is a high pressure in the southern hemisphere, so circulation looks like this. And here's Antarctica. What that means is that basically you have flow enhanced westerlies. Okay. Antarctica. I have a high pressure here, right? I have anomalous flow in this direction, right? Okay, what does that mean for upwelling, by the way? Southern hemisphere. Southern hemisphere, stress that way, flow this way, upwelling or downwelling? Upwelling, right? Okay, good. So I have flow going this way, unusually strong flow going this way. I have offshore transport. The water down comes from below. And what's the temperature of the water? Don't answer if you know this question. What do you think the water temperature below is compared to the water temperature of the surface? Everywhere else in the world, it's colder, right? But here, it's actually warmer, right? The water below is warmer than it is at the surface. And that's because buoyancy down at these temperatures is controlled by salinity, not by temperature. So the water below is actually warm. So if I bring up more water from below, I'm bringing up warm water from below. A lot warmer, about 1.5 degrees warmer, right? So you have this wind here, and we'll come back to this. If I look at mid-troposphere, like 5 kilometers up in the atmosphere, I also see a high pressure here. And if I look at 200 millibars at tropopause level, I also see a high pressure. And the amplitude increases as I go up. This is something that, you know, if you have atmospheric science 101, you think equivalent barotropic. This is a signal that's not forced because sea ice is changing. It's actually an atmospheric circulation anomaly that's causing sea ice changes and causing ocean and wind changes. So it's what we call equivalent barostructure, with hints here as you go aloft that there's something going on in the tropics. Okay? So if we look at, say, here, right offshore here of these glaciers here that are retreating really fast, right? If I look here at the winds, the longshore winds, this is the climatology from the 1980s to through the 1980s, and it's basically no wind to speak of. And then in southern hemisphere winter, you have westerly anomalies, which is upwelling, right? And then it comes back down. And this is in 2 different data sets. That's what happens in the 1990s to 1999 period. And so you still have the upwelling here, but the upwelling now goes all the way through here. So you have a much longer upwelling season where you're just bringing up warm water from below. It's not as simple as that you're just lifting warm water up. It turns out there's tidal mixing on these really rough shelves, and it's really nasty oceanographically. But there's been some really nice modeling work on that shows that this works. So here's the period where you've just enhanced the wind stress for an extra 3 months, right? And so you just have more upwelling going on climatologically for 1 decade compared to the previous decade. So unlike in the 1980s, in the 1990s, upwelling favorable winds, especially in fall, lifted warm water up from the deep onto the continental shelf, where it was transported onto the grounding ice sheet, right? Coincident with the time these glaciers started to accelerate. Could be a coincidence? Probably not. So here's now the correlation between wind stress again here. So this is just looking around, and this is the sea level pressure. So here's this high pressure here. So when I have stronger wind stress here, I have a high offshore, which gives me stronger westerlies. Here's the same thing at 200 millibars. Here's this high right above this high, right, which tells me I have this deep structure in the atmosphere, which tells me it's not forced by the surface. It's actually forcing the surface. And then if I look at how it was correlated with surface temperature, I see this warming here in the central tropical Pacific. And I think, I know this, right? El Nino does this for me, right? I know when I have unusually warm water there, I have teleconnections, and they look like this, okay? So I'm going to show you that in a second here. Oh. So here's a kind of a efficient way of saying, I want to understand the relationship between changes throughout the tropics in the world in sea surface temperature and circulation in the southern hemisphere. So it's a mathematical technique called Waxham covariance analysis. It says, find me the patterns that maximally covary between circulation in the southern hemisphere and tropical sea surface temperature. And it picks out, the first pattern is El Nino, as you expect. Right? El Nino has these teleconnections down to both poles. Right? But here's one. The second pattern shows you warming in the central tropical Pacific. Here's Australia, here's South America. Warming here is associated with high pressure in the tropics. Okay, we know that. This is at 200 millibars tropopause level. Low pressure here, high pressure here, low pressure here, high pressure. You can see this kind of train here, right? Great circle route, right? So it's coming out of this place where you have warmer water than usual, which means you have more rainfall, which is expanding the air more than usual here. And here are the time series of these two patterns. This is a tropical sea surface temperature pattern. The other one is a tropical circulation pattern. You can see they're really highly correlated, 0.82. And there's this trend, positive trend. So this is the kind of trend pattern you've seen over this 35-year period, right? 25-year period, okay? Okay, all right. So what we did then is we said, okay, and let's turn this around. We said, okay, let's take sea surface temperature here and correlate it with circulation. And what do we get? So if I correlate sea surface temperature there with 200 millibar circulation, I find out high, low, high, right? That's the great circle route. So it's telling you that even on month-to-month timescales, you're seeing this. When it's unusually warm in this region here, because this is after we removed the trend, right? So they're just saying we see this on month-to-month timescales, we see it on year-to-year timescales, and we see it in the trend. When it warms here, you get this teleconnection pattern down here, this Rossby wave train. So the southern hemisphere circulation appears to be forced by the tropics. And if you then take the time series of either one of these patterns and you regress it against sea level pressure, which is the contours here, sea ice concentration, which is the red and blue colors, red meaning less, blue meaning more, and temperature, surface temperature, brown mean warm, green mean cold, you get this pattern here. So look at this pattern for a second. It says this trend here, basically, or the year-to-year variability, when I'm positive, when I'm more in this warm phase here, what I see is I see unusually high pressure here off of West Antarctica, where the circulation looks like this. So I have more westerly flow. With a circulation that looks like this, I'm pushing sea ice this way, right? I'm pushing it inshore, so sea ice concentration goes down. Right? This is all observations, right? These are all observations. And if I'm blowing unusually strong winds this way, I get more sea ice here because I'm just blowing it away from the continent, right? Same thing here. If I look at here, I'm blowing wind onshore, so it's warmer than normal here. I'm just advecting warmer air from lower latitudes. And here I'm advecting cold air off the continent, right? So it's just colder. So everything looks, in terms of all the trends that are observed, in terms of sea ice, in terms of air temperature, right, and even in terms of ocean water temperature down below, seems like it's all being forced by local wind changes, and the local wind changes are being forced by the tropical Pacific. Okay. Okay. Why am I going this way? There we go. Okay, so here we go. There we go. So now we said, okay, let's take that sea surface temperature pattern and we'll put it under an atmospheric climate model, and we'll just say, what are the anomalies that result when I force an atmosphere model with these sea surface temperature? And the answer is high, low, high, right? You get the observations, which is kind of a proof that actually, in fact, the amplitude is right too. It's not just the pattern is right, but the amplitude is exactly what the observations tell you, which tells you that the trends in the winds that are causing more warm water to come up in Antarctica, which is destabilization, are forced by trends in the tropical Pacific sea surface temperature, right? This is not global warming in the sense that CO2 is increased, you have more surface melt. It's not global warming in the sense that CO2 increased and the water temperature locally has become higher, right? There's trends in the tropical Pacific for whatever reason that are causing the ice sheets to be destabilized in West Antarctica. Okay. You even get the right sea level pressure patterns here. You get the right warm anomaly patterns. In our model, we don't have any sea ice moving, so we can't say anything about sea ice, but it's consistent. So the conclusion is the recent fall and winter trends in West Antarctica circulation and air temperature, as well as the zonal wind stress that is implicated in the melting and retreat of the Antarctic ice sheets, are likely due to trends in the tropical Pacific sea surface temperature. Yeah?
Was that just a single model, or was that kind of the model ensemble mean?
That model result there was a single model, right? It was a single model.
Why did you choose that model and not one of the others? Is that the one model that worked?
No, because it's the one the guy who did the calculations for me is most familiar with, and he could, and we had model runs around to actually look at this already. It's not what we did the runs for, but we could actually just look at it. Yeah. Yeah. I don't know if anyone's done it in other models, but everything just physically makes sense. And that pattern that I showed you is a pattern that models reproduce when you put in El Nino anomalies, which basically move convection from the Western Pacific to the Central Pacific. So it'd be surprising if all models didn't do it. It'd be really surprising if all models didn't give you that. Okay. Here's the El Nino pattern of wind anomalies. You probably can't see this. The main thing is down here in West Antarctica. With El Nino, so warming in the Central Pacific, you get this increased westerlies here off of West Antarctica. So, you know, we already knew that this was a causal thing from all the experiments that the community had done with various models looking at the impact of El Nino in both hemispheres. 2011 was an interesting year because it was a La Nina year, which means the winds should have been more easterly than normal, and voila, there's the wind anomalies in 2011. Here's Pine Island down here, and it's got unusually strong, unusually weak westerlies, right? Easterly anomalies, which means the upwelling anomalies are this way, right? The up Ekman transport's this way, which means there's downwelling anomalies in 2011. And if you look then here in Pine Island in this corner, this is the temperature of the water at the base of the ice sheet. This is the ice sheet boundary. So everything here is an ice shelf that's floating on the ocean. This is the temperature of the water underneath the ice shelf. And the red is greater than 1.2 degrees Celsius. This is 2009. So you're on this upward trend, right, of warming here, increased westerlies in this region here, increased upwelling, warmer water. This is what happened in 2011, and poof, you know, just the winds turn around, you have anomalous easterlies. So you have less upwelling than you had 2 years ago, and the temperature drops, and now it's only minus 0.1, right? So the temperature has dropped a degree C, just because the winds were unusually weak. The westerlies were unusually weak. Right, so there's a lot of evidence that the temperature at the base of these ice shelves, which is controlling if the ice shelves are stable or not, is forced by wind anomalies that are forced by the tropical Pacific. Okay, so let's look at the Arctic. How am I doing on time, by the way? Okay, good. Oh, one quick look. If you look and say, what do the seedmate models tell me about how the last 25 years should have evolved? This is the observed wintertime southern hemisphere trends in sea surface temperature, and there's warming through this whole region here and kind of nothing going on here. And this is what the CMIP models tell me. They tell me it should be warming everywhere in the tropics. Okay, so the CMIP models don't get this, right? They didn't predict this for this 25-year period. Let's go now to the Arctic. So here's now the trends in annual average temperature. So it's like an all seasons, not just winter southern hemisphere. Again, here's this warming horseshoe that you saw even in June, July, August. It's cooling here. Some people call this a hiatus. I'm not going to go there. Okay, but it's cooling here. It's warming here. And it's warming in the Arctic big time. I mean, really record rates of warming in the instrumental record. This warming actually here is due to loss of sea ice. So you're basically just in the wintertime taking what used to look like land, which is easy to cool in winter, and replacing it by ocean, which is impossible to cool, right? So there's a big warming here because sea ice is being lost. But over here, that's not the case, right? And this warming here is on the order of 0.7 to 0.9 degrees C warming per decade, which is massive. Like that's 10 times the global average temperature warming, right? Really record warming in the Arctic, Greenland, Northeast Canada. So then if I look now, so this is the, oh yeah, by the way, the colors here, this color scheme is, go back, nothing happened. This is like a dead spot here for the clicker. There we go. Red is warm and blue is cold in the ocean. Brown is warm over land areas and sea ice areas because they're such different amounts. This is 0.7 to 0.9, whereas these numbers here are 0.2. So you could just see the ocean ones. We just colored them differently, but there we go. So that's the same pattern for the surface. If you look, say in the troposphere average temperature, you see something also really cool. Over Greenland, this region here where it's warming at the surface, it's actually warming the whole troposphere. And if you look at 200 millibar, the tropopause level, it's really high, unusually high. And that's the biggest feature in the whole planet in terms of circulation changes in the upper troposphere. It's right there. And again, this is a pattern that's it's warm, it's warm, it's warm, right? The atmosphere is just stacked vertically. It's equivalent barotropic. That's not forced by changes in what's going on at the surface. That's not what the answer would look like. That's got to be forced from the tropics. You look at that and say, got to be from the tropics. Right? If it was forced at the surface, the maximum warming would be at the surface and it would decay as you go up. And by the time you got to 2000 to the tropopause level, you'd see nothing. Right? So this is really clear evidence that this is not forced by the surface, but it's actually forcing the surface. Okay, and then there's this quantity, just call it wave activity flux, which is telling you where information is coming from. This is a trend. And can anyone see this? Can anyone pick something out here? There's a feature here which is interesting. I want you to find it. Here we are. Here's North America. Here's Greenland. Colors here now, don't worry about the colors, what they mean. But there's arrows here. You see any kind of interesting feature? Great circle, right? And the great circle starts from Central Pacific, right? This is basically telling you where information is coming from. So there's basically been a trend that actually has information going up here. And these circles here are basically, you can think of as places where you should accelerate or decelerate the flow. So they're associated with high and low pressures. So this is really strong evidence that the trends over the Arctic, especially over Greenland, actually are forced from the tropical Pacific, just like the ones in Antarctica. Right? So here's again that technique of saying, oh, give me the patterns that maximally explain the covariance between two different fields. The first set of patterns that come out is just El Nino. It's warming here in the eastern Pacific. And then associated with that warming, convection is moved out here. So I have high pressure, low pressure, high pressure. This is the PNA pattern that we're all familiar with. Here's a time series of these two patterns. And they go up and down with, there's an El Nino event, there's an El Nino event, there's an El Nino event. 82, 83, big one. 96, 97. But there's no trend there. But if you look at the second pattern that comes out, it's warming over here, it's cooling over here, it's warming over here, and you see this bingo, this Rossby wave train, right? This is observations. And look at the time series of these. It's low, and then it goes high, right? So it just says basically this pattern here is the change. It's a change that you see. In fact, this is basically the change in terms of the amplitude even. It's 20 millibar, 20 geopotential meter increase in the height field at the tropopause here, which is exactly what's observed. So it's explaining all of the trend is explained by this pattern, which seems to begin to be linked to what's going on in the tropical Pacific. Okay? So mode 2 captures the observed trends. There's the arc. And there we go. Roll it up again. So the wave train is equivalent barotropic. The EP flux vectors flow along a great circle route from the tropical Pacific to the Atlantic. It's associated with precipitation anomalies in the central Pacific. It's the same story. You know, it's just the northern hemisphere flip side of what's going on in the tropical Pacific. It's a classic response from the tropical Pacific forcing that comes out of a paper in 1983 and hundreds of papers thereafter. Okay? So this is the same atmosphere model forced by those observed trends, right? And here's the observations again. This is right here. This is the surface temperature changes, the troposphere temperature changes, and here's the tropopause temperature changes. So here's this Arctic amplification here over Greenland in the Arctic, and here's this wave vector. But I just want to point out, here's what happens when you force the ECHM atmosphere model with the tropical Pacific sea surface temperatures that are observed in this pattern. They just are taken from this. You end up with warming at the surface here between about 0.5 and 0.7 degrees. You end up with warming in the troposphere, which is about 0.4 to 0.5 degrees, and you end up with a tropopause increase of 15 geopotential meters. Right? This is, and here's the EP flux. It's not quite as clean as the observations, but you can see them coming out of here and coming over this way. Okay, so again, I get this stacked structure, right, which is what you expect. And the amplitude is about 2/3, whoops. I'm going the wrong way here. Okay, the amplitude is about 2/3 of the observed. So you can say 2/3 of the observed circulation changes in the warming that you're seeing over Greenland in northeast Canada today are due to tropical Pacific changes. They're not due to increasing CO2, unless increasing CO2 changes the tropical Pacific. Right? Okay. So mode 2 captures the observed trends. The warming is observed in all seasons, but is greatest in winter. Locally, the wave train resembles the NAO pattern. It's a negative phase of the NAO of 0.7, but the physics is very different. The NAO represents interaction between storms and the mean flow locally in the North Atlantic. This is actually a pattern that looks like the NAO, but it's actually forced from the tropical Pacific, and the physics of it is very different from the NAO. So it's not the same physics, but it looks like the NAO. Okay. What do the climate models say? Well, this is what the climate models say. Over this time period here, it should have warmed everywhere in the tropics and really warmed a lot in the high latitudes. It should have warmed a lot everywhere in the troposphere, but particularly in the tropics, and should warm most in the tropics. Right? And you don't see this stacked bullseye over Greenland, right? At all. It's gone. Right? So without this unusual pattern of warming here and cooling here, you don't see Antarctica changes, and you don't get Pine Island changes, and you don't see the Greenland and Arctic changes, right? But with them, you see them both, right? Okay, so the model fails to capture the observed trends in temperature and circulation over Arctic and Greenland. The CMIP models. Oh. Yo! Okay, wait a minute. How do I... I need to get back like to... Try that one there, maybe. No, it's every time I hit the back button, it keeps moving forward. Actually, yeah, that's good. That's good. That's good. I think it'll work.
While you're here,
yeah.
The EUF, the time series from the EUF analysis here for the sea surface temperature only goes back to 79. But presumably, you could extend that analysis.
Yeah, you could. You could. Yeah. Further, so in the northern hemisphere, we can go back farther. We can look at different decades. But
what I'm saying, well, my question is though, is you kind of have this stable mean state, and you have a short period in the 1990s at the transition,
yep.
and another stable state.
Yeah.
So
oh well, I don't know if they're stable state, but we definitely have in the tropical Pacific. You definitely have the 80s look different than the 90s, which look different than 2000. So if you look at the tropical Pacific sea trends, they tend to go up. They tend to be kind of warming up to maybe 1999 or so. They're kind of flat and they warm a lot, and then they kind of come down from 2000 to present. They come down again. So it gets colder in the East Tropical Pacific. So I want to talk about that because I don't know why that's there. Okay, good. That's good. So that's where I'm going to go next here. So what are the hypotheses for the recent multi-decadal trends in the tropical Pacific? Because if you want to, I mean, I think I would be willing to bet many cases of beer on the fact that what you're seeing mostly in Antarctica today and mostly in the Arctic today is due to changes in the tropical Pacific. Now the question is, why did the tropical Pacific do what it did? You know, why did kind of 80s seem to be sort of what we call normal, and then like through the late 80s to maybe the late 1900s, 1990s, it got really warm and then it kind of got cold again. It's getting colder again. Why is that the case? So one hypothesis is that the observed recent multi-decadal regional trends in these high latitude things is due to anthropogenic forcing, and that if the impact of the changes in the CO2, right, and all the aerosols and everything have caused trends in the tropical Pacific that force those patterns, right? Now, based on everything I've shown you, would you say that that's a false or true hypothesis?
False.
False, right? I mean, clearly, not only does the ensemble mean not get it, but you can't find a climate model in that period that actually got it. Not one, right, got that trend pattern. So you'd say, well, okay, yeah, it's false. So it's taken at face value. I think that's the next thing. The results from the CMIP-5 model suggest that this hypothesis is false. However, the response of the CMIP-5 models may be corrupted by errors in the models, including biases in the mean state and or errors in the aerosol forcing. Right? So it could be that the aerosol force is not put in right, and if you put it in right, you actually get this pattern. It could just be that that the biases in the mean state mean that you don't have ENSO. And if you don't have ENSO, the biggest difference could have been that you had these really big ENSO events in the 90s, and then since 1990, you've had none. And that just could be random sampling. I mean, think about it. If you have 3 El Ninos in one decade and 2 in the next, then the anomalies, the change, the trend, is just 1 El Nino divided by 20 years, right? And it looks like an El Nino. And that's kind of what the pattern looks like, right? It's cooling in the east, a little bit of warming in the west. It's not exactly. Some people call that pattern the Pacific decadal oscillation. Most people think the Pacific decadal oscillation is just debris of ENSO. So then you're stuck, because if it's debris of ENSO, none of your models have good ENSOs. You can't even address that question, right? So the other one is the observed recent multi-decadal trends in the Antarctic and Arctic are due to internal variability, such as debris of ENSO. 3 El Nino events one year, a decade to the next, right? Or ENSO-independent multi-decadal variability in the tropical Pacific. It may exist, right? There's ideas on the table. None of them are defendable because the data aren't good enough to do it. But there's potential for multi-decadal variability that looks like that pattern that has nothing to do with increases in CO2. Right? But you're kind of stuck because you can't ask the climate model, what does your decadal variability look like, when in fact the interannual variability looks so bad to start with. You can't really believe the decadal stuff, right? So the CMIP-5 models have either poor ENSOs or no ENSO at all. Only 2 of 25 models have ENSO variability that does not violate the robust observational constraints. The temporal and spatial structure of the multi-decadal internal variability in the CMIP-5 models we have examined does not resemble that in nature. So if you just go back to those CMIP-5 models and say, let's forget about CO2, let's just look at the decadal variability in the tropical Pacific in these models and say, does it look like the observed trends that we're seeing? And the answer is no. Okay. So how do you actually determine whether it's actually a response to CO2 forcing or just natural variability? And you're kind of stuck if you're going to just live with the CMIP-5 models because they're inappropriate for addressing this problem. And it's kind of interesting because if you go back to when I was a graduate student working on El Nino, strangely enough, everybody knew this was a problem. So everybody actually, what we called flux corrected your climate model. We actually put in artificial fluxes to make the climatology real. And when you did that, most models gave you a really good ENSO. Not a surprise, that's what theory suggests, and that's what most models did. So what happened between 1995 or 1990 and today is that IPCC said, no more flux corrections, can't do that. You know, it's like they're not in the real world. The response to increasing CO2 might be different if you flux correct the model than it would be if you didn't flux correct the model. That's true, right? But what I do know is if you don't flux correct a model, you lose ENSO, you lose ENSO variability, you lose anything that has to do with ENSO or the residuals of ENSO, and you lose the ability to address these questions like, why do you have those trends, right? So what you've thrown out, you know is a problem. What you potentially do in terms of damage, if you nudge, is the response might be sensitive to nudging, right? Or flux correcting, I guess we call it nowadays. But I mean, that's you got to live with one of those two things. Either you don't address issues of attribution of regional climate change, and you don't make predictions about how the climate's going to change in your place in space in the future. You just make predictions about how the global average temperature is going to change. Great, I'm happy that IPCC models are right models for you. But if you want to ask the questions like, what's going to happen to the Greenland ice sheets? What's going to happen to the Antarctic? What's going to happen to the Southwest U.S.? What's going to happen in Indonesia? Then you're really in a bad spot. The present-day climate models are inappropriate for those questions. So first, here's the approach that we're trying to sell. I think other people are starting to sell this now too, so hopefully it'll catch. Test the third hypothesis. That is, the large biases in the climatology of the tropical Pacific in the 20th century simulations using the CMIP-5 models renders unrealistic internal variability, and so, for example, and therefore unrealistic patterns for the response to anthropogenic climate change. So we can actually test this, because we can take an IPCC climate model, we can flux correct it at the right climatology, right? And we can say, does it give you a good ENSO? And the answer is, we've done it in 2 models, the answer is yes. Not a surprise, like I said, in 1990, that's what everybody did, and it almost always worked. So you can flux correct the model to give you good ENSO, and to even give you good decadal variability that we see in the observations, right? We still don't know why the decadal variability in the models does what it does, but it looks like observations. Yeah?
Can you briefly explain how flux correction works?
Yeah, so the way some people did it, and probably even including me, I can't remember, was you would actually just add an equation to all your terms that look like this. Like, let's say this is your time rate of change of temperature, and let's just say this is for the sea surface temperature. You'd have all these terms over here: advection, mixing, radiation, you name it. But then you add this kind of other term here, which is this, which always drags, where T star is a prescribed quantity. So I just have this field that I read into my climate model, which is the observed climatology. So when the model, say, gets too warm compared to the observed climatology, there's a term here that drags it back, right? That's one way to do it. It's not a good way to do it, because it means if I force the model somewhere else, this term is always going to be trying to drag it back to the, so that's not good. So IPCC was right in saying that you can't do that. But I could do something else here. I could just add another flux. I can just say, okay, I've got my coupled model. It calculates everything, and it tells me the Western Pacific is 2 degrees too warm. I can make an estimate and say 2 degrees, I'm going to need about 10 watts per meter squared to suck out of the ocean to make it the right answer. And there's a little guess there, but I can do that. So I just add this F here. Let's say it's 10 watts per meter squared, right? All the time, right? To my model. And it's going to say, I'm just going to keep on, just have a perpetual cooling, because, and maybe it's there because I don't have enough clouds, right? And so I get too much sunlight. And I'm just going to put this in there, and it's going to cool it down, right? Now I can do my climate change experiment, and I can still run away. I can get a runaway greenhouse, and this is still going to be 10 watts per meter squared, right? It allows the climate to shift. So this would be called nudging, because you're trying to put it back to the present climatology. This would just be called a flux correction, right? And that's what we're doing now, and that's what most people are doing now. So you still allow the climate to go wherever it wants to go. It's just that you put in an artificial hand of God to create a climatology to start with that looks like Earth. Okay, so hence the CMIP-5 models are inappropriate for detection attribution studies of multi-decadal trends in the Antarctic and Arctic, and how ENSO will change due to global warming. Okay, if that's true. And like I said, we've done this and it works. So Now we have models that actually produce good ENSO. The same IPCC model that was really bad now produces a good ENSO. Okay, so now I'm way past where I want to be here. How do I get out of this? These are extra slides. I wasn't even going to go here. Okay, like a little bit more, like maybe one even more of that. Let's try this one right there. Yep, 5 minutes. Good. I'm close to the end here. Okay. Hypothesis 2. The observed recent multi-decadal trends are due to internal variability such as debris of ENSO. Okay. So here again, the climate models don't give you ENSO, so you can flux correct them to get the right ENSO. Yeah. So test the third hypothesis. Okay. Okay. Hence the multi-decadal trends. Okay. Here we go. How to test these? Testing. Fix the models. Hard, right? The people are trying to fix these problems since I was a beginning graduate student, and they're actually worse today than they've ever been. Well, it's because you improve the models, you improve resolution, but it doesn't mean that you've actually fixed the places where there's problems. And we know that the coupling between the tropical Pacific atmosphere is really tight, right? So small errors in one when you couple are amplified, right? And if you have small errors in both of them, you couple, you know, things go all over the place, which is why you get double ITCZs and all sorts of weird stuff when you couple. You can nudge the models to the present day climatology, which is what I'm going to do. Then analyze the ENSO variability in the models that have more realistic mean state. Is the internal variability consistent with nature? If yes, then you can test the second hypothesis, which is where we're at right now. Are the recent multi-decadal trends consistent with the internal variability hypothesis? And at least this one model we've looked at, the answer is yes. Okay, so this same climate model that didn't have good ENSOs and didn't have good decadal variability when we compare it to, say, the PDO pattern, whatever the physics is of that, when we nudge it, and it gives us, one, a better ENSO, and it gives us better decadal variability that looks like the observed trends. So now you can't, at least in this model, you'd say, I can't rule out the hypothesis that that's what we're seeing in the Arctic today and what we're seeing in Antarctica is just natural variability. Right? It's still possible that the increase in CO2 in the aerosols are pushing us towards this pattern that looks a heck of a lot like the natural variability in this model. And this is only one model. If we nudge all the other models to give us good ENSOs and we ask them what's the decadal variability look like in the models, does it look like the observed? I don't know. If the answer is, yeah, they all look like the observed, that's a pretty strong statement that mostly of what we're seeing right now on a regional basis is natural variability. Okay? Okay. Then you can do that last hypothesis, which everyone is interested in, is redo the 20th century simulation using the debiased models, compare the force trends to those observed. Are the recent multi-decadal trends consistent with what's expected due to the anthropogenic forcing? And then, of course, you can go to the future. What will happen to ENSO? Because you have a model now that has ENSO. So redo the 21st century projections. That's the path that we are proposing that all climate modelers take in addition to the IPCC runs they're normally going to do, is redo the same runs with a flux corrected version of your model and see what happens. Here's one indication, this is the last slide, that says that this matters. This is 7 different couple of models. This is what happened to the El Nino in that model. Purple is the GCM. What happened to the El Nino in that model compared to the 20th century El Nino, and one means no change. This is the sampling error. So no change, little bit change, no change, little bit change, no change. Well, quite a bit of increase. Not that this is the right answer, but this is saying, turning around and saying, I know that the observed mean state matters. So that the ENSO in this model doesn't look anything like the real world ENSO. So what does it mean to actually plot this up here? I'm comparing this model's whatever. They call it ENSO, but I could call it a zebra. It's the same thing. It's different than ENSO. This model's zebra to the zebra in the future. This model's elephant to the elephant in the future, right? Maybe this is the model that has an El Nino today. It looks like El Nino. I can say this is how the El Nino changed in that one model. But I don't think actually any of these 7 are the ones that actually did it right. Okay. But I could turn around and say, I have this offline model, which is really beautiful. Given me the mean states of the tropical Pacific atmosphere and the ocean, does it reproduce the observations? And the answer is yes, it reproduces all of the robust atmosphere if I just add some stochastic forcing, some weather to it. It reproduces everything in the observations. And I can say, I'm going to take the mean state changes that came out of the GCM, and I'm going to put it into that offline model that I know has a good ENSO. looks like the real world, and say, how does ENSO change? And the answer is, ooh, it changes a lot. So this is just a statement that where you start from matters of what the response of ENSO is going to be, right? And there's no consensus here, but the point here is that the sensitivity of ENSO to these mean state changes is much bigger if you start with the real world beast, right? And this is not surprising. This is exactly what was expected from theory in 1976, Steve Zebak's thesis, right? So there's a lot of reason why you want to actually go this route. If you want to do detection and attribution studies, if you want to understand what's going on regionally in climate in the 20th century or in the 21st century, you really got to address this problem that you have to get the natural variability right, in particular in the tropical Pacific, because it explains so much of the world's climate variability. Thank you. Yep.
Sorry, 10 minutes ago. But
Sorry.
An important question. I'm showing my ignorance here. Is there a simple reason why Western Europe is the only part of the globe which is not impacted by this?
But by El Nino?
Yeah.
Yeah, the simple reason is that information likes to go along great circle routes given the scale of the temperature anomalies. So basically, it kind of peters out as you go off the east coast of the U.S. And the volatility of the Atlantic storm track is so large because of the way the North America looks. That's a longer story, but you have a very volatile North American storm track that really overwhelms any kind of El Nino signal that you could get over there, even if you could get one over there. So yeah, it's a perfect place. If you don't want to see El Nino, go to Europe.
My students, is there a course I can go to? I've never been able to explain this to myself and my students.
Can you send me an email? I mean, the classic paper in this might not be easy to read, but it's all in this classic paper by Hoskins and Caroli back in '79, maybe? Yeah.
Thanks.
So trying to digest the implications of this. So in the Arctic, we're seeing the sea ice fall off a cliff. And in the Antarctic, the sea ice extended duration is not really shifting much.
Uh-huh.
Is that simply down to the tight connections to those two locations from the tropical Pacific?
Well, I'm not sure why the Antarctic sea ice hasn't changed too much. There's a lot of possibilities on the table. That teleconnection pattern I showed you is a regional phenomenon, so it affects things from the Antarctic Peninsula to the Ross Sea, basically, right? So it doesn't explain the rest of the Antarctic or why sea ice is doing what it's doing. In the Arctic, remember I showed you two patches. There's one up in the, what is it called? It's the Barents Sea, which has been a lot of sea ice loss. You cannot attribute that to El Nino. But if you go over northeast Canada, and as I've argued here in Greenland, you can explain it by trends in the tropical Pacific. So this really strong warming you see in those regions, right? Probably even the changes in the ocean temperature and ocean circulation around the fjords that bathe Greenland are probably explainable by trends in the tropical Pacific. But it's a little bit, you can wire that diagram to explain why there's more heat transport going into the Barents Sea that might melt sea ice, but it's a little bit, we haven't done that yet, but it's possible. It's possible simply because there's this paper by, I don't know if you're familiar, by Hatoum et al. He was looking at the NAO and how much heat and salt is transported into the subpolar gyre, right? Roughly speaking, the more heat and salt you transport, the more ice is going to melt back, right? He found that in the negative phase of the NAO, there's much more salt and heat going up in the subpolar gyre, right? Now that's what this thing does over the, at least over the Labrador Sea region. There's a high sitting over Greenland, which is kind of like the negative phase of the NAO. So one thing we're looking at now is, do you get the wind patterns that you see at the surface, these trends? And the answer is yes, you do from the tropical Pacific. But then the question is, if you put those winds on an ocean model, do you see more heat and salt coming into the North Sea? If that's the case, then you can explain the trends in sea ice in the Barents Sea due to the same pattern, tropical Pacific, right? But those are changes in ocean circulation that are moving more heat up, which is why as you go up above that, you don't see any temperature anomalies in the atmosphere because it's all due to the changes in sea ice, which might be linked to the tropical Pacific, but we haven't done those yet, that calculation yet.
David, the speed up of Klein Island and all those ice streams is, that's like one of the something that is actually genuinely quite worrying.
Yeah,
and
yeah,
scary, right? And
yeah.
a bunch of glaciologists say, like, this is a potentially irreversible process on particular content.
Yeah.
You know, this is just going to go. So if that's potentially driven by this kind of multi-decadal trend, this decadal trend in the Pacific, and if that Pacific trend is something that will just rock back and forth every few decades, why hasn't Pine Island gone before?
It might have.
It might have.
Yeah, we just don't know. We don't know. I mean, the people are trying to get at these records from either looking at changes in the surface mass balance and stuff like that, and isotope composition of the ice over time. It's a really hard thing to do, but we don't know. But it's this. If this is right, there's reason to believe that these things became stabilized every once in a while in history. Like, you know, it's still true that once you melt off, it goes back and finds that next ridge line, right? And to get it back out there is a really long haul, right? Because you have to buy up a lot of ice and push it back out. But yeah, there's no reason why this shouldn't be going on all through history. So it does raise the question of, are these the things we want to put out there as the charismatic climate animals that we're worried about global warming? I'm not so sure we do.
Yeah, I mean, do you know, can you see a whole series of former branding lines?
It's out of my expertise. I'm not going to, whatever I'd say would be wrong probably, or at least uninformed.
What started ENSO in the first place? You know, 3 million years ago. Why then? What was it?
Oh, I didn't say it started. I said we know at least happened till at least back then. We just don't have records before then. But what you need is a place to pile up water in the east, right? And in the west, right? So when you have these normal trades, you need. I mean, if you start really moving around continents at a big scale, like 50 million years ago, then you know all bets are off. But you need to create a basin that's wide enough and blocked at both ends. And blocking doesn't take much. Just 10 degrees around the equator is all you need, right? So you could throw away most of South America and North America, and you still have ENSOs, right? All you need to, in fact, the Galapagos is kind of really the end of the tropical Pacific. The stuff that goes on from the Galapagos to the coast, it doesn't matter to the atmosphere. It matters to the ocean, but not to the atmosphere. So what you need is, you know, anything, if we knew, for example, when New Guinea drifted into the equatorial zone and was on the equator, that would be telltale. Because before that, if New Guinea was south, the cold tongue ends somewhere off of India, you know, like south of India on the equator. And actually, the first ocean model that was run, why they did this is gone. Oh, I know. Islands were expensive to put in your model. So they sank Indonesia and they sank New Guinea. And of course, the cold tongue went from the Eastern Pacific all the way to just south of Ceylon. Well, it's not called Ceylon anymore. It's called Sri Lanka, thanks. And it was like a blast from the past. Okay, so you know, like it's like anything you want to look at in the ocean in those two basins was like it was wasted. You know, like a whole year's worth of computer time because they wanted to sink some islands because islands were expensive to integrate around, and those are the two they choose. You know, they could have sunk Australia and it wouldn't have mattered, but you know that one was not a good one to sink. So yeah, if something, you know, whenever New Guinea drifted into that equatorial zone, that would be a big deal. Same thing actually is true with, you see some telltale signs. Galapagos wasn't always where it is, and it wasn't always that high. If it was actually just 2 degrees south of where it was today, the cold tongue would go another 1,000 kilometers to the east. So there's some, you know, really some cool records from that area if you could get them, like sediment cores, because there should have been a really profound change when Galapagos drifted north onto the equator. Yeah.
So this might be a naive question, but you didn't really mention the Indian Ocean at all.
Yeah.
And
or the Atlantic.
So that must mean that although there is connections between them, they're not that.
No. In fact, on a year-to-year timescale, if you look at what goes on in the Indian Ocean, it's mostly forced by El Nino. And what happens is the Walker circulation strength changes. And so unlike in the Pacific, when it gets warm, it rains more in that spot. In the Indian Ocean, when it gets warm, it's dry, which tells you it's warm because it's sunny, right? And it's getting more sundown. And why it's sunnier is because El Nino moves around the Walker circulation. And when you have La Nina events, so the Walker circulation convection is far in the west, you have really strong sinking in the, where's it go? So the other way around. When you have El Nino and you have a really central Pacific sinking region, rising region, the sinking is right over the heart of the Indian Ocean, and it gets warm there. So the warm water gets warmer water, but it's being driven by ENSO.
And so there's like sort of striking monsoons and things that doesn't sort of feed back into.
It does, but it's all small. I mean, it's all. Well, I mean, of course, when you go to increasing CO2, you don't really know what's small. I mean, it could be that changes in monsoon actually do come back to haunt you with El Nino, but you know, the links today between El Nino and the monsoon circulation are really, really weak, right? And in monsoon, I mean like Indian Ocean monsoon. There's a link between the Atlantic and the Pacific. I mean, it's mostly the Pacific drives the Atlantic again, although the Atlantic has its own El Nino phenomenon. Actually, it looks, in the physics, is the same as the Pacific. It's just that the basin is smaller, so the restoring time in the ocean is smaller. So it's just a wimpy El Nino. The events are just weaker, but it's the same physics.
And sorry, just one last question. So isn't there a sort of optimal size at which point the Pacific becomes dominant? So as the Pacific has grown as a basin, does it reach a point where it calls all the shots?
Certainly it's big enough now to call the shots. If you make it bigger, it's kind of interesting. You can start to get weird things going on that don't look like El Nino. They're still coupled things, but they start doing other things like this mobile mode I mentioned, which is a destabilizer. If the Pacific were big enough, you would see these things truck along there. You wouldn't see what we see today as this whole eastern and central Pacific warming kind of in force and then cooling. You'd see things propagating like they do in some climate models. Yeah.
Okay, I'm trying to think this through. The context of the decadal changes is still taking place against what's happening with CO2.
Yep.
So one of the things in the future might be how those things interact.
Yeah, exactly. Yeah.
And somebody asked about the recovery phase of something like the ice shells and
Yep.
surfacing. So is there any research or concern or idea there about the contextualization of these decadal changes against what we know is happening with CO2 and temperature?
Well, yeah, I think people are, I mean, IPCC is more and more interested in this kind of attribution and detection based on natural variability. And also, there's been strong arguments, I think really coherent arguments, saying that the response due to climate change should project onto these natural patterns of variability. But of course, if you don't have them in your model to start with, you won't get those responses. So people are worried about it. I mean, people know it's a problem, and people worry about it because they think it's probably the way climate should respond. There's been overall warming, and these patterns that we see nowadays that are there because of basic geometry, like the geometry of the NAO is there because of the Rockies in the shape of North America. And basically, once you have that, you can't not have an NAO, right? And you can't not have a storm track that tracks from southwest to northeast. And those are hard things to get rid of, right? And with an increase in CO2, you find out any changes in circulation are really subtle, you know? The only place you expect big changes in circulation are ENSO, and you can't address that question. I mean, the theory suggests that. And the theory suggests you don't have big changes in storm tracks. And that's what the observations are telling us so far. We don't really see any changes in storm tracks. At least not that you can actually say you can attribute to any forcing, just natural variability.
Any question?
Okay, thanks.